We have three offerings currently. One's a premium solution, extremely low noise figure, great linearity. Another one will be slightly cheaper solution. Will still be 2 satellite receiving, and not as expensive, but also slightly degraded performance, slightly degraded noise figures, slightly degraded out of band attenuation. And then the third option is going to be a single satellite receiver that will be even a little more cheaper. Right now, our current reference design caters to GPS because of our customer demand. And we basically, a breakdown of what the circuit looks like is we have band L1, band L5. Both of these on our reference design should be, when incorporated into a customer's application, will go through customer derived probably couplers to connect to a dual receive antenna. And from our job at Guerrilla RF is we give you a best noise figure possible from that point. So the first thing the signal will see are RF360 Qualcomm SAW filters. Extremely low loss, really good out of band attenuation. And the out of band attenuation is great for co-located environments such as shark fin antennas, anything near a cellular signal or a Wi-Fi signal. You want to have good out of band attenuation to not let those signals interfere with what you're trying to filter out, which in this case are the GNSS signals. So after the first SAW filters, we enter into a Guerrilla RF low noise LNA. Our current LNAs of choice are 2070X variety. 2073W is a very popular automotive LNA. 2071 as well. The 2073 has a little bit more gain than the 2071, whereas the 2071 has a slight better noise figure with less gain. But the 2073 seems to fit the bill so far. And after the 2073 LNAs, we then have on our reference design contingency for attenuation. We can build T or pi attenuators to balance the gain coming out of those first stage LNAs. So you have band L1, band L5. Band L5 is always going to be a little bit higher in gain than band L1 because 1175 megahertz lower in frequency has a slight bit more gain through our LNAs than 1575 megahertz. So to balance that, we add attenuation to keep when both signals go through our centered diplexer, they both have equal gain when they arrive at that point. So when you measure the output combined 2 humps signal of band L1 and band L5, the gain should be within half a dB or better of each other. And to accommodate higher gain solutions where someone might have a long cable loss, we can put a very flat response broadband gain block as a second stage after our first stages, after our diplexer. So once both signals are combined, they have equal gain. They can both enter our broadband gain block, such as our 2010, our 2012. Those right now are our main ones that we're using. And those will both give you a boost of anywhere between 8 to 12 dB of gain. And then furthermore, we have more pi attenuation we can add after the second stage to knock down the gain so that at the output going to the transceiver or going to the computer in the car, you can have the gain value that you desire. There's also lots of considerations besides gain, because gain for us is actually really easy, and that is noise figure and linearity. Many people want their input IP3s to be as high as possible. So we try to get our input IP3s 0 dBm or higher. And our noise figure so far is not a problem when combining Qualcomm's SAW filters with our low noise LNAs. The noise figure will be dominated by the first stage filter and the first stage LNA. And we are very happy to say that we're at least very well below 2 dB noise figure for both of those, if not below or around 1.7 dB. And for this type of cascaded circuit, that noise figure is really good. Besides our Cadillac solution where we can receive band L1 and L5 separately, we're developing a newer, lower cost solution where we don't use two separate circuits and combine them through a diplexer. What we do is we put the diplexer first. So band L1 and band L5 can go into a diplexer, the same one that we use on our current solution, which is on our website. That then combined receive signal, which has not been amplified, then goes straight into our GRF 2073W or 2071 or 2074, whichever one we decide is the best for your solution. After the amplification in our LNA, we then have a dual hump filter, and then we give provision if somebody needs more gain than what we can provide with a one-stage solution. We have an optional second stage, which is easily brought into the circuit using 0 ohm resistors to either go through a bypass trace or feed the signal into the second stage. And this solution, we think, will have trade-offs such as maybe slightly degraded noise figure and definitely degraded out-of-band attenuation. Our provision for any signals that are critical where the out-of-band attenuation is too high, as in not enough, we have provisions for notch filtering using discrete components such as shunt LC circuits. We can, if we see a signal that is encroaching, being amplified from some other source, is providing power that we're amplifying that we don't intend to, we can notch it out. And that's one of the powers of we like with our discrete solutions rather than than using a module. We have lots of options to customize tunes to customer needs. And unlike a cell phone, typically a GNSS solution, like I'm talking about, we typically have a lot more EVB room to play with, and we don't need to live in the land of modules. A third new solution that we've been looking at is a single satellite receive, where somebody would use an GNSS antenna that only has one pin, where you pick up everything, and we would receive just maybe one satellite, and then we could separate that through a dual hump filter, a pre-LNA filter, which we get through Qualcomm. Then we would amplify the filtered out signals, which would be really low. And then we have a post amplifier dual hump filter. And in this way, we can provide a solution that is not as accurate, but is lower in cost. Not everybody needs two receives. A single source GNSS antenna can give you accuracy between 5 to 10 meters. So if you're only receiving one satellite source, you can get accuracy of 5 to 10 meters. If you have a dual source, such as band L1 and L5, your accuracy increases between 3 and 5 meters. So if you're implementing in your car a GNSS circuit like we offer using bands L1 and L5, your location, if you're sitting in a parking lot, you're most likely going to be somewhere nearby where you're really located in that parking lot. If you use a cheaper solution that maybe just incorporates one satellite receive, you may be in the parking lot in the back of a building, but your map on your car, your heads-up display may show you being in the front of the building, or maybe a building over from where you're actually located. We don't include currently on our discrete designs an ESD component. All of the whenever I help customers integrate our circuits on their boards, they typically have an 042 or like an 0603 size ESD diode, and I tune their reference boards with that diode in place to make sure any contribution, if there was any at all, would be accounted for. I don't know if that's something we could implement on our BOM here. I don't know if that would help, but typically we don't use an ESD. The only thing we really do is just DC blocking caps for voltage, to protect from voltage going into any of our amplifiers where it's not supposed to.
Thank you so much for watching. If you'd like more information, please email us at sales@guerrilla-rf.com. And don't forget to subscribe to our channel for more content from Guerrilla RF.